Hi everyone! So today we're going to be talking about magnetic flux, magnetic induction, and the working principle of a transformer. Alright, I hope you're ready guys. Physics is fun! Physics is fun guys! Alright, so here we have two kinds of transformers and today we're going to be talking about the ugly cylindrical block. And no, I'm not talking about Optimus Prime. And now that ugly cylindrical block on the right actually has a lot of uses and is found in almost all of our electrical appliances, such as transmission lines, our normal circuits, and even our phone chargers. So without further ado, let's delve into transformers.
The cube, boy. Get me the cube.
First of all, I'm going to talk about Faraday's law of induction. It is introduced by Michael Faraday, which is the man shown in this diagram. Faraday's law of induction is a basic law of electromagnetism that predicts how a magnetic field will interact with an electric circuit to produce an electromotive force, which is also known as EMF. It is the fundamental operating principle of transformers, inductors, and many types of electrical motors, generators, and solenoids. Faraday's experiment shows that EMF induced by a change in magnetic flux depends on only a few factors. First, EMF is directly proportional to the change in flux. Secondly, EMF is greatest when the change in time is the smallest. That is, EMF is inversely proportional to the change in time. Finally, if a coil has n turns, an EMF will be produced that is n times greater than for a single coil, so that EMF is directly proportional to n. The equation for the EMF induced by a change in magnetic flux is shown in this diagram, which is here. And the relationship is known as the Faraday's law of induction. The units for EMF are volts as is usual. As you all see, there is a negative sign in the EMF equation. The minus means that the EMF creates a current and magnetic field that oppose the change in magnetic flux. And this is known as this is defined by the Lenz law, which is introduced by Heinrich Friedrich Emil Lenz, which is the man in this diagram. In simple words, Lenz law can be defined as the direction of induced EMF always oppose the change in flux that produced it. Next, I'm going to talk about transformer. So the type of transformer considered here is based on Faraday's law of induction. This is a simple setup of a transformer which is made of soft iron core and iron coil. The two coils are called the primary coil and the secondary coil. In normal use, the input voltage is placed on the primary and the secondary produces the transformed output voltage. For the simple transformer shown in the diagram, the output voltage depends almost entirely on the input voltage and the ratio of number of loops in the primary and secondary coils. Faraday's law of induction for the secondary coil gives its induced output voltage V subscript S as Vs equals to negative N subscript S, which is the number of coil in the secondary coil, times delta phi, which is a change in magnetic field, over delta t, which is a change in time, where n. Note that the output voltage equals the induced EMF, provided coil resistance is very small. The cross-sectional area of the coils is the same on either side, as is the magnetic field strength. So the change in magnetic flux is the same on either side. The output primary voltage Vp also related to the changing flux by the equation V subscript P equals to negative N subscript P times delta phi, which is the change in magnetic flux, over delta T, which is change in time. Taking the ratio of these last two equations yields a useful relationship, which is the ratio of the secondary voltage to primary voltage is equals to the ratio of number of secondary turns to the number of primary turns.
What is an induction? One of the biggest discoveries is that electric current can create magnetic fields. But the question is, can magnetic fields create or induce magnetic currents? Induction is the ability of the magnetic field to create current inside a conductor. Hans Christian Ørsted already showed us that if you have a current in a wire, it creates a magnetic field. So we know current can create a magnetic field. But Michael Faraday, a scientist, wanted to know if a current can be produced from a magnetic field. He wondered if the opposite was true. This apparatus shown was used. When the switch was closed, a little current is generated and it moves slightly to the right. When the switch is opened, the same thing happens but with the left. That is induction. But he wondered why it only happened when he opened and closed the switch. It's because of flux. What is a flux? Flux, better known as magnetic flux, is how a conducting material is affected by the magnetic field. Magnetic flux is going to be the product of the strength of the magnetic field and the surface area perpendicular to that magnetic field. This is an example. This is a loop with magnetic fields going through it. The magnetic field before the switch is closed is 0. But if magnetic field is added, there will be a change in magnetic flux. Thus, there's an electromotive induction. It created current. The next example has more magnetic fields going through it, as shown here. Once magnetic field increases, there will be more magnetic flux and more current. The equation for magnetic flux is magnetic field multiplied by a cross-sectional area which is perpendicular to that magnetic field. Another example here is shown. There are two loops of wire with multiple magnetic field lines going through it. If you compare both wires, the one on the left will have more of a magnetic flux compared to the right, as there is more magnetic field lines.
What is back EMF? Back EMF is a changing magnetic field inside a coil will induce an EMF in that coil that opposes the change in current that produced this change in magnetic field, and therefore in the opposite direction to the applied voltage. When you apply a voltage to a coil, the current doesn't reach its steady state value immediately after you apply a voltage. It forces the current in the coil to build up gradually. Initially, the current is 0, but the current starts to flow in the direction of the applied voltage. Hence, the resulting change in current θI points in the same direction as the applied voltage. Next, we got eddy current. In reality, the electrical energy is not all conserved. A lot of it is converted into heat by eddy currents. In a transformer, the magnetic flux created by the primary coil induces a current in the core. This occurs in order to oppose the charge that produced the magnetic flux. The currents flowing in a core are called eddy currents. These currents produce heat, using our energy and so causing inefficiency. One way of minimizing the effects of eddy currents is to make the core out of iron laminate. This is layers of iron separated by thin layers of an insulator, such as varnish. The amplitude of the eddy currents produced is reduced, as the current cannot flow through the layers of insulator. Next, what is magnetization of iron core? The core loss usually refers to the material itself, and absorbing some of the magnetic field energy, as it is magnetized and demagnetized. Soft magnets such as iron is a lot easier to get magnetized or demagnetized compared to hard magnets such as stainless steel. Next, what is leakage flux? In ideal transformer, all the flux will link with both primary and secondary windings. But in reality, it is impossible to link all the flux in transformer with both primary and secondary windings. Although maximum flux will link with both windings through the core of transformers, but still, there will be a small amount of flux which will link either winding but not both. This flux is called leakage flux, which will pass through the winding insulation instead of passing through core. Due to this leakage flux in transformers, both primary and secondary windings have leakage reactance. This phenomenon in transformer is known as magnetic leakage.
Alright, just wanted to get your attention. I hope that scared you awake. Now, this is the final segment of our video, so just hang with us for a little bit, alright? Now, transformers, also known as voltage transformers, are devices used in electrical circuits to change the voltage of electricity flowing through a circuit. Transformers can either be used to, let's see over here, step down or step up. And today, right now, we're going to look at the applications of a transformer. And the first application which we're going to look at is, of course, the use in your mobile phones. Now, devices like mobile phones and other small devices and applications, these need a smaller potential difference than the 230 volts from the mains electricity. Therefore, they need a step down transformer to reduce the potential difference built into the plug or power supply. Now, switch mode transformers do this by using complex electronic circuits. I'll explain what switch mode transformers can do. Complex electronic circuits are not really in our syllabus, I think. So just remember that these are neither parallel nor series circuits. Alright, got that? Neither parallel nor series circuits. Now, these rapidly switch the currents on and off, allowing the alternating current to be changed to a higher frequency, and this is often done between 50 and 200 Hz. At these frequencies, there is a much smaller and lighter transformer than normal, which is able to reduce the potential difference, and as a result, these transformers are suited for use in power supplies such as mobile phone chargers. When the device is plugged in and the batteries are charging, a load is being applied. And this is another advantage for using switch mode transformers in applications such as the mobile phone chargers, because one of their size, two because of the step down transformers, and three because of its rapid changing currents, which is switching the currents on and off at a high frequency between 50 Hz and 100 Hz. So another application of transformers is its use in transmission lines, which is inevitably how you get your energy at home, which in turn results in how you get energy for your Wi-Fi, which is your life. Sad face. Now, energy is lost in the process of transmitting energy long distances, such as during the journey from a power plant. Let's say a power plant is here to your home. Let's say these power lines are buzzing with energy. Alright. Now, less energy is lost if the voltage is very high. So electrical utilities use high voltage in long distance transmission wires. So high voltages are transmitted along these lines. But high voltage is too dangerous for home use. So electrical utilities use transformers to change the voltage electricity as it travels from the power plant to you. Let's say you. First, the voltage of electricity coming from the power plant is stepped up using step-up transformers for the right level for long distance transmission. Later, the voltage is stepped down, before it enters your home, once again using transformers. Now, in order for the electrical power distribution network to function, voltages must be stepped up, before power is transmitted great distances over power lines. So you see here, these power lines, and shown in the picture, can travel for miles and miles and miles and not reach anything in the process. So a lot of heat is lost. Yeah, so one of the major problems is that power is lost between the power plant and consumers because currents use some of the power to heat up the transmission lines. The power transmitted along the line is equal, let's say power along the transmission lines is equal to the voltage times the current. The higher the voltage, the lower the current that must flow within the transmission lines to deliver the same power. Lower currents produce much less heating and much less power loss. Of course, high voltages must be stepped back down before the power is supplied to our homes. Transformers are critical elements that step down and step up the transformers at each end of the transmission lines. Alright guys, that's the end of our presentation. Thank you so much for watching. I hope you've learned something about transformers and you've been transformed. Okay, thanks, bye.